Familial adenomatous polyposis presents in adolescence in many cases, and talking to people at that age presents particular problems. To try and illustrate this, we made a funny video some years ago where I had to play the part of a teenager with familial adenomatous polyposis. See what you think.
Hello, Mrs. Hasselborough. Come and take a seat.
Hello, Dr. Gunn. Oh, nice to see you again.
You brought John with you?
I've brought John, yeah.
Hiya, John.
Saturday
Have a seat.
school to come.
Now, how are you getting on?
Oh, we're all fine. Our Johnny's a bit worried about all these tests, you know, after his dad died on your ward with them polypus things.
Yes.
But I said you would talk to him about it today. I mean, you won't talk to me about it.
You haven't explained the tests.
No, well, I
at all.
don't really know what they're involved. I know they're a bit nasty. I've told them they're a bit nasty, but I actually don't know what's involved.
Well, John, you know that your father died with a tumour in his bowel, and that it's possible that you may have that same disease. Had you understood that?
It's been told to him. He just doesn't listen to anybody.
We can do tests to tell if you've got this disease or not by finding out if you've got polyps in your bowel. If you have, then we can offer some treatment which should prevent you getting the tumour that your father had. So, would you be willing to consider tests that would tell if you're going to get a tumour and lead to treatment which would prevent you getting the tumour? How do you feel about that?
He'll come, whatever you organise for him, he'll come. I'll make sure he comes.
Would you be happy with that, John?
Yeah.
But talk to Dr. Gunn then.
Right. Aye.
The big problem is, John, that the tests, or at least one of the tests, isn't pleasant because it means examining your back passage with an instrument. It doesn't hurt, but it isn't pleasant. So to do that test, I'd have to pass an instrument into your back passage. It would only take a few minutes. It would, however, let me know if you had polyps in your bowel and if you require any treatment or not. How do you feel about that?
Go on then.
Well, if you are willing, I would like to do the test sometime, which would take 2 or 3 minutes. We could tell if you had polyps, and then I could discuss any treatment with you, depending on whether or not you had the polyps. I would suggest that you could go home, talk this over with your mother sometime, and then if you'd like to undergo the test, you could come back and see me, we could talk about it again. The test would only take a few minutes. Would you like to do that?
Aye.
Would you be willing to come back and talk about it again in about 3 or 4 weeks' time?
You'll come back, Dr. Gunn. He probably won't talk
Right.
to you. He doesn't talk to anybody.
Mm.
Look at him.
Well, the decision is yours, John. If you'd like to undergo the test, I'd be very pleased to perform it, and then we could talk about whether or not you require any treatment to prevent you getting this tumour. Anything you would like to ask me at all?
No, it's all right.
Right then. So make an appointment to see me in 3 or 4 weeks' time, John, and I'll talk to you about the test again.
Okay.
I'll just make that appointment with the nurse on the way out.
Yes,
do I?
please.
I'll make sure he comes back.
Right, thanks for coming along, John.
Bye, Dr.
Bye.
Gunn. Thanks.
Sometimes we have to explain rather unusual names of syndromes and diseases to families. One of the most difficult ones is hereditary non-polyposis colon cancer, or HNPCC. We made this little clip to illustrate how difficult it is to explain this to a patient.
Well, hello, Mrs. Higginbottom, and welcome.
Hello, Dr. Doscopy.
Now, I heard from my old friend in Edinburgh, Malcolm McTartan, that your brother had had problems, had a kidney tumour. I'm sorry to hear that, but I was glad to hear that he successfully removed it. But apparently he had a couple of skin cancers called BCCs. So he did some genetic tests, and it turns out there's an inherited cause for the problem. Now, it might affect you, so we need to think about some screening tests.
What sort of inherited problem is it?
Well, we call it HNPCC. It's a bit of a mouthful, so let me just explain what that means. Now, the H stands for hereditary. Now, traditionally, we call things that run down through a family from one generation to the next hereditary.
Yeah, but our parents, they lived till they were really old. They went on safari on one of those saga holidays and they got killed by a stampede of elephants.
Well, yes, it's a bit confusing, but it doesn't have to be hereditary to be called hereditary. You see, your parents could have been non-penetrant.
Well, they never had any problems of that sort.
No, you misunderstand. I mean, genetically speaking, they might. One of them might have been a carrier.
Yeah, oh yeah. Actually, I've got a friend who's a carrier of cystic fibrosis. Her baby died, but Ethel, she's a carrier. She's fine because she's just a carrier.
Yes. Yes. Yes, that's true for cystic fibrosis. You see, cystic fibrosis is what we call a recessive trait, and if you carry a recessive trait, it doesn't affect you. It's only if both parents have it and they both pass it on, the child gets it. So then you can get brothers and sisters affected, and we call that familial. But HNPCC, that's hereditary. Okay? Anyway, let's move on. The NP stands for non-polyposis, and that means that your brother didn't have familial adenomatous polyposis.
That's recessive.
No, that's dominant.
But you said...
I know. Well, the thing is that the surgeons who originally named it didn't understand the difference. Familial adenomatous polyposis is hereditary.
But he didn't have it.
No.
And why mention it?
Well, because we knew about that first, and it causes inherited cancer.
Cancer of the kidney.
No, of the bowel.
And why mention it?
Well, because that was the first type of inherited cancer that we knew about.
Cancer of the kidney?
No, cancer of the bowel.
Then why?
No, never mind. The important thing is that your brother didn't have familial adenomatous polyposis, and you don't either. At least you're no more likely than I am to get familial adenomatous polyposis.
Well, what's the CC stand for?
The CC stands for colon cancer.
But my brother had kidney cancer.
Yes, but in fact it's more likely that he gets colon cancer, and in fact you might get colon cancer, so we need to check your colon.
And my kidneys?
No, just your colon, because the kidney type is quite rare, so we don't check for that.
So I might have hereditary non-polyposis. That thing. So I need my colon examining.
And your uterus.
Uterus?
Well, yes, because if you carry this, then you might get endometrial cancer. That's what we call cancer of the uterus. In fact, that's actually, if you're a woman who carries this, you're slightly more likely to get endometrial cancer than you are to get colon cancer.
Well, why don't we call it hereditary endometrial cancer?
I really don't know. But that's the way it is, so I think let's just move on, shall we? So we need to organise for you to come in for a colonoscopy and to have a scan of your uterus. Okay?
Right. It's complicated, isn't it?
It is, yes.
Yeah. So I might have this HNPCC.
Well, you might have, because your brother hadn't, and it's a bit of a mouthful, as I know, as you can see. So if you like, you can call it Lynch syndrome, because that's its other name.
Oh, Lynch syndrome! I've heard about that. That was that family that was in a journal I read once. A family called Warty or Warfin or something from America.
That's right.
She was a laundry woman or something, and the
That's
doctor realised that all her family had cancer.
The second classic form of Mendelian inheritance is autosomal recessive inheritance, where a faulty copy of the gene is inherited from both parents. Selena, Dominic, thanks for coming. My name's John Byrne. I'm a consultant in clinical genetics, and I've been asked to have a chat with you because of the problems with the baby that you lost. Can I ask what the baby was called?
David.
And how long is it now since David died?
6 weeks.
Okay. team that looked after David sent some samples in to us and also did several investigations, and we know that we know the cause for that now. So what I'd like to do is explain to you why David died, and then answer any questions that you might have. But before I do explain, can I ask what questions do you think you might like an answer to?
Well, firstly, obviously, why and how, and if there was anything we could have done to prevent it, and secondly, will it happen again?
Yeah, sure, okay. Well, first of all, let me explain what it was that David had. David had a condition called spinal muscular atrophy, and that means that the little nerve cells in his spinal cord, which drive the muscles, stopped working. Now, we all make these little relay stations down our back so that the messages from our brain can get out to our muscles. And as we're developing in the womb, most of the cells die away, leaving just these key cells to act as relay stations. Because of the spelling mistake in the gene, David didn't keep the relay stations, so those cells died away, and that made him very weak because he couldn't move his muscles properly. And in fact, sometimes children live quite a long time, but he got a chest infection because of his inability to cough and move his muscles, and that's led to his infectious, very severe infection, and that led to him dying. Now, we know the cause of this because it's a very well recognised diagnosis. It's what we call an autosomal recessive trait. Now, just to explain that in a little bit more detail, we all carry our genes in matching pairs with a copy from mum and a copy from dad, and it works out that every one of us has at least one gene that's got a spelling mistake in it, but usually we get by on the spare copy, so we never know. But now and again a couple will marry who both carry the same spelling mistake in the same gene, or at least a spelling mistake in the same gene that stops one copy working. So that's what's happened in your case. So in each of you have one working copy of this gene, which is fine, and the other one which has a spelling mistake in it. And each time you have a pregnancy, it's a 50-50 chance whether you pass on the working copy of the gene or the one with the spelling mistake. So there's a 50-50 chance that the egg will get the faulty copy of the gene, and there's a 50-50 chance that it will meet a sperm that also has the faulty copy of the gene. So each time you get pregnant, there's a half chance of it coming in the egg and a half chance of it coming in the sperm. So there's a quarter chance, a 1 in 4 chance, that you'll end up with 2 faulty copies of the gene, and then the baby will have the same problem.
That's
But
just
we
for
could
the spinal thing. That's that
Just
David
for spinal
had.
muscular atrophy. Otherwise, you're just the same as everybody else.
But we could have a faulty one from Dom and a healthy one from me, or vice
Absolutely.
versa, and
That's
the baby
right.
would be fine.
That's right. So in fact, the good news is that in fact there's a 3 out of 4 chance that one of you or both of you will give a working copy of the gene, and the baby will be fine.
Mm-hmm.
Now we do know, and you asked whether it would happen again. The answer is it's a 1 in 4 risk. The next natural question from that is, well, would it be the same? Would it be as bad? And the answer is it always is a pretty bad condition. If you've got the full-blown disorder, it'd be very unlikely that the baby would survive long term if you had another baby that was affected.
So if it hadn't been that infection that had killed him, it would have been something.
It would have
else.
just been failure of the respiratory system, and the baby just would have, David would just gradually become weaker and unable to breathe.
But it's possible that the baby could go to full term and be born, and then
Oh, yes.
die in early life.
Yeah. Now, the good news is that we actually know from the tests that were sent in what the precise spelling mistake was. So this is something that we can test a future pregnancy for. So when you get pregnant, we could bring you in at 11 weeks and take a sample from the afterbirth to see whether the pregnancy is affected or not.
And there would
that
then be
gives
the
you the
option of
chance of
termination.
termination of that pregnancy. You don't have to. You might just say, well, we'd like to know, but I wouldn't want a termination. That's a decision you can take yourselves, but the important thing is that option exists, and that's something that you might want to talk about. A lot of people use diagrams when they're explaining single gene inheritance. I prefer to use my hands for the simple reason that I can carry on looking at people. If I'm using my hands in this way, I'm watching their reaction, and people sometimes don't understand, and you can do it again. If you start drawing diagrams, you're not looking at them, and therefore you don't get that feedback. All children are tested at birth for phenylketonuria, a particular autosomal recessive inborn error of metabolism that can be treated by a special diet. it's not uncommon to be asked to counsel families affected by PKU, and occasionally it's necessary to counsel a parent who carries this condition. Selina, Dominic, it's a pleasure to see you. My name's John Byrne. I'm a consultant clinical geneticist. I was asked by your doctor to send you an appointment. Can you tell me, was it your idea or the doctor's idea that brought you here?
Well, it's a bit of both, but it's our idea really. I've got PKU, and we've been planning to have a baby for a while, and we obviously are concerned because we know that I have it, but we want to know what the chances are of passing that on.
So PKU, or phenylketonuria, is a recessive trait. That means that you inherited the spelling mistake from both mum and dad in your phenylalanine hydroxylase gene, to be precise, and it means that you can't chemically process a particular amino acid from the proteins that you eat. So you have to have this not very nice diet that you've had all your life and you've tolerated. Because if you get given phenylalanine, you can't break it down and deal with it properly, so it accumulates in your bloodstream, and if you hadn't been picked up as a baby, you'd have been brain damaged by that and have been left very severely autistic and unable to speak. So the good news is that this is a treatable condition, but it's not much fun, as you've experienced. Now, we know that you inherited that from your mum and your dad, so they were both carriers. They had a 50-50 chance of passing it on. They passed it on to you, so you've actually got two faulty copies of this gene, one from mum and one from dad. So every time you have a baby, you will make a carrier of this condition. You cannot avoid that. The baby will inherit the problem from you. Selina is, I think, not related to you in any way. You're not cousins or connected in any way. So you're just like me, a general member of our population. Now, we know that the incidence of this condition is about 1 in 10,000. So about 1 in 10,000 babies are born with phenylketonuria. And that means that the chance of you being a carrier, and I could explain it to you mathematically if you want me to, is about 1 in 50. So about 1 in 50 of the population are carriers of phenylketonuria, which is a bit higher than you'd expect, actually. It's quite surprising. But in fact, all of us carry something, and it's not uncommon to be a carrier of a recessive trait. In fact, probably everybody carries at least one of these things, and this particular one is about a 1 in 50 chance. So that means there's a 1 in 50 chance that you're a carrier. So that kind of means there's a 1 in 50 chance that you're both carrying it, if you see what I mean. So each time you have a baby, the baby will get the gene from you, from Dominic, because he has nothing else to give. And if you were a carrier, it would be a 50-50 chance whether you passed on your working copy or your faulty copy. Okay? Now there's a 1 in 50 chance that you're a carrier, so there'd be a 1 in 100 chance of the baby getting it from your side of the family. That's a half of you, right?
How do we find out if Selina's a carrier or not?
Well, let's come back to that in a minute. Let's get the numbers right first, because that's quite important. So there's a 1 in 50 chance that Selina's a carrier, a 1 in 100 chance, therefore, that the baby would inherit phenylketonuria from Selina, and a guarantee that it would inherit it from you. So there's actually a 1% risk of the baby being affected.
Right.
Okay. Now, the answer to your question is we don't have a test for this at the moment, although we might be able to do some work on a DNA sample from Selina. It's actually looking for a bit of looking at a needle in a haystack, and it's not an easy test to arrange. But in fact, the truth is the odds are pretty heavily on your side, because if you turn that around the other way, if there's a 1 in 100 chance that you are going to have an affected baby, that means there's a 99% probability that the baby will not have phenylketonuria. Okay?
Right.
So that's actually pretty good odds.
Yeah.
It's not a guarantee. It's slightly higher than the general population, obviously, but it's still a small risk. Okay? When you're talking to a family affected by a recessive disease, it's often necessary to think about the carrier frequency in the general population. That can be calculated if you know the frequency of the particular disease using an equation called the Hardy-Weinberg equilibrium. This clip explains how we work out the carrier frequency using that formula. When we saw the couple with the recessive disease, we said that Dominic had phenylketonuria, so he was bound to pass it on, and that Selena had a 1 in 50 chance of being a carrier because she was from the general population. Have you any idea how you worked that out?
No, in a word.
Okay. Now, the reason it's important is because we get lots of different diseases, and people often ask, what's the chance of someone being a carrier of this or that condition? And you can work it backwards from knowing the condition's frequency in the population. There's actually a very famous formula. It's called the Hardy-Weinberg equilibrium. And it's, I'll tell you it, and then I'll explain how it works. So the formula is P squared plus 2PQ plus Q squared equals 1, which is a completely unhelpful piece of mathematics. So what it means is that there are 3 types of people in the population. There are the people who don't carry phenylketonuria, there are the people who have phenylketonuria, and there are the people who carry phenylketonuria, where they've got one version of the gene and one working and one faulty copy of the gene. And if the gene has a frequency of 1 in 100, then the chance that you will have 2 copies of it from a gene pool is 1 in 100 times 1 in 100, which is 1 in 10,000. If you have a 1 in 100 gene frequency, the chance of you being a carrier is 1 in 50. Let me explain how that works. I'm going to tell you a true story. About 20 years ago, I was sitting reading the paper when my wife dumped a lot of damp socks in front of me and said, put those into pairs. And I was tired of doing that, and I had a very brilliant idea, I thought. So I went to the shops the next day and I bought a large number of identical pairs of black socks. And I went home, took all my existing socks out, put them in away, and I put my identical socks in the drawer, all loose. And I said, I never have to put my socks in pairs ever again, because I just have to take any 2 out and they'll match. Brilliant. Didn't quite work because the dye sort of wears off after a while and they all change colour slightly. But it worked for quite a long time. The only slight problem was at that time I had a job in London quite regularly. I had to catch the 7 o'clock train to London. So I had to get up and get dressed in the dark because Linda wouldn't let me put the light on. And so it occurred to me one day going to the train that I might just possibly get up and put a black sock on one foot, but one of my training socks on the other foot in the total darkness, because I had 1 pair of training socks in that drawer as well. And I thought, what's the chance I'd go to London wearing a white sock? So here we have my sock drawer, and in it are lots of black socks and the occasional white sock. So the question is, what's the chance if, let's just say for example, 1 in 20 of the socks in my drawer were white. What's the chance that I would go to London wearing a white sock?
You'd have to take into account.
So that again, there's a 1 in 20.
So 1 in 20 of the socks is a white one.
Yeah.
What's the chance I go to London wearing a white sock?
So is that, well, you've got a 1 in 20 for each foot.
Yeah, that's right. So there's a 1 in 20 chance for having a white sock on your left foot and a 1 in 20 chance of having a white sock on your right foot. There's a 2 out of 20 chance of getting one or the other. That's 1 in 10. It's twice as high, right? So if you put your hand in here and pull out a sock, then it might be a pair of black socks. It probably will be, but now and again you'll pull out a white sock. What's the chance if 1 in 20 socks is a white one? What's the chance of pulling out a pair of white socks?
Is it?
That's hard mental arithmetic. I'll let you off.
1 over 20 times 1 over
Exactly,
20. Yeah.
that's right. So there's a 1 in 20
Showing
chance
me
you'll
up.
have a white sock on your left foot, and a 1 in 20 chance you'll have a white sock on your right foot. So there's a 1 in 20 times 1 in 20, or 1 in 400 chance that you would have a pair of white socks on. Now you could get clever and say when you took out the first white sock, you reduced the chance of getting a white sock out of the drawer because there's not as many white socks in the drawer anymore. But that's just being difficult. Let's imagine it's a very big drawer. So then what you're saying is that there's a 1 in 20 chance of having a white there being a white sock, 1 in 400 chance of a pair of white socks, 1 in 10 chance of being a carrier. In other words, if you know how many people get on the train wearing a pair of white socks, if 1 in 400 of the people getting on the train is wearing white socks on both feet, that must mean that 1 in 20 of the socks in the drawer was white. And you can predict
Right.
that
It has
1
a
in
knock-on
10 of the
effect.
people, you work backwards, right? So if you know how many people got a pair of white socks, you can work out the gene frequency, and from that you can work out the carrier frequency. The square root of the frequency times 2.
Right.
The Hardy-Weinberg equilibrium. X-linked inheritance presents particular problems in genetic counselling, given that it can run for many generations without being spotted in a family. This next section deals with the classical issue of Duchenne muscular dystrophy running in a family. Selina, Dominic, welcome. My name is John Byrne. I'm the consultant in clinical genetics, and I've been asked to have a chat with you about, I think, Selina's family history. Can I ask, first of all, was it your idea or your doctor's idea that you came to the genetic clinic?
It was my idea.
Yeah, you're right.
Yeah,
My idea. I asked to be referred. We are wanting to start a family as soon as possible. But I do have concerns in that my brother died at the age of 23 from Duchenne muscular dystrophy, as did my uncle, my mother's brother. And I know that it's genetic, but wanted to come and see you to find out the specifics of how exactly that works and to share that with Dominic. And really what the chances are of it being passed on to our potential child.
Okay. Before I go into that, I mean, are you thinking of starting a pregnancy in the near future? Are you pregnant already?
Not pregnant, don't think,
Okay.
but we're thinking about it.
All right.
Yeah.
Okay, fine. Well, you're quite right. Duchenne muscular dystrophy is a very well recognised genetic condition, and the fact that your mother's brother had it, and sorry, what was your brother called?
Michael.
Michael. I know from our records, in fact, the family had been looked after by us before, and that Michael had classical Duchenne muscular dystrophy, as did your uncle. So, in fact, that makes the counselling fairly straightforward, and I'd like to run you through that. But just, I'm going to take you back a step to explain how genes work, so it makes sense out of this. So, we get our genes in matching pairs, copy from mum and a copy from dad. And a gene's an instruction, tells you what colour your eyes are going to be, or how many fingers you need, or whatever. And there are several thousand of these genes passed on to us. Now, we have 2 copies of everything except the genes that are carried on the X chromosome. So genes are strung together on chromosomes like beads on a string. So you get 2 copies of every gene, you get 2 copies of every chromosome, with the exception of the sex chromosomes, where men and women are different. So women get 2 X chromosomes, men get 1 X chromosome, and a little thing called the Y chromosome. And the Y chromosome is what made Dominic male. The problem is, the Y, it kind of sort of makes you male, then lies around feeling proud of itself for the next 70 years. It doesn't do much. And so you don't have any significant number of genes on it. So it means that any gene on the X chromosome, a man only gets 1 copy of, whereas a woman has 2 copies of it.
Right.
Now, to balance the books, women actually switch off 1 or other X in each of the cells in their body. So, in fact, it's a little bit more complicated, but essentially you've got 2 copies, and so at least half of the cells in your body will be using a working copy if one of them's got a spelling mistake. Whereas if you're a man and you get a spelling mistake, you have no other copy. So every cell in your body will have the faulty copy of the gene, and you've got no cover. So you will get a full-blown problem. Okay?
Is that, in simple terms, if I happen to give birth to a boy, he is more likely to suffer from Duchenne as opposed to if we have a girl, because she would have.
That's right. And if you think about it, we know that your uncle had Duchenne muscular dystrophy and your brother also, so we can be confident that your mother was a carrier of Duchenne muscular dystrophy. Okay? Now, you are the sister, and so you inherited 1 or other of your mother's X chromosome. So it's a 50-50 chance whether or not you are a carrier or not a carrier. Okay? When you come to have your children, it's then a 50-50 chance again whether you pass on the working copy or the faulty copy if you are a carrier. Does that make sense?
Yeah.
So there's a half chance that you're a carrier, and if you're a carrier, there's a half chance of passing on the spelling mistake in the gene.
Right.
But then there's only a half chance it will be an affected baby, because Dominic would have to make it a boy with a Y chromosome.
Okay.
So in fact, the odds are actually quite strongly on your side.
Is there any way we can find out if I'm a carrier or not?
Absolutely, yes.
Right.
And so what we will do is go back to the sample that we stored, because in fact your brother, with great foresight, asked to donate a sample of his DNA, and we're going to go and find the spelling mistake in the gene. And assuming we can do that, we will test you. Even if we can't, we can use markers in his X chromosome to see whether you got the same X chromosome as he did from your mother. Yeah? So even if we can't find the precise spelling mistake, we'll be able to track down whether you are at high risk or not of being a carrier.
Okay.
And then if you are a carrier, then it becomes a straight 50-50 chance whether you pass on the working copy or not, and a 50-50 chance whether it's a boy or a girl. So there's a 1 in 4 chance that you would have an affected boy, a 1 in 4 chance that you would have a boy who was fine, and a 2 out of 4 chance that you would have a girl who may or may not be a carrier.
Okay.
Now the girls typically don't have a problem. Very occasionally they will show some problems, because I told you it was a 50-50 chance in each of your cells which X you switch off. So you could have just by chance switched off all of the X's that carry the good copy of the gene and only used the X's that had the spelling mistake, and if that had happened you would have had some muscle problems too. It does happen occasionally. So it does present us with a little bit of a problem on a pregnancy test, because if it was a girl who was a carrier, you might argue that that child might be slightly affected, but it's extremely unusual for a girl to present in childhood with a problem. If anything, it tends to be a much later onset weakness and a much milder problem.
And you say they choose one, they switch on. Do they ever change?
No, once you've decided in each cell line which one's on and which one's off, it stays the same.
For the rest
So
of
you
your
may,
life.
it's called a mosaic, because if you looked at the cells in Selena's body, you'd find a 50-50 mix of some using the X that came from dad and some using the X that came from mum, and it's sort of just mingled together.
Which is why you inherit personality traits from both mum and dad.
Well, yeah, but that's slightly different, because personality traits, of course, are determined by lots of other genes, not on the X chromosome.
Right.
So in fact, they aren't part of this story. But yes, so it's a similar sort of issue about mixing genes. You've got 2 copies of everything, so and you're a mixed of the 2. Mitochondrial inheritance is a particular problem because it's so difficult to make accurate statements. But nevertheless, increasingly we are recognising families affected by mitochondrial disorders, and it's important to be able to deal with this in the clinic. Selena, Dominic, welcome. My name is John Byrne. I'm the consultant clinical geneticist. I've been asked to have a word with you by the paediatric team who have been looking after your little boy David, because they've done some genetic tests and we've got to the bottom of the problem, and they thought that you might want to come and have a chat to discuss that. Did they discuss that very much with you before they referred you, or did they just sort of send you over to see me?
They sent me over to see you, but also I'm obviously interested myself because we would like to become pregnant, and I'd like to know what the chances are, knowing that I have been pregnant 7 times with 4 different partners, and only one of those pregnancies has gone to full term and has survived, even though David is obviously profoundly disabled. We'd like to know what the chances are of that happening again.
Okay. David's problem is a very rare condition called Lee's disease, which is a breakdown of development of the brain, and as you know, the prospects are very poor. Because of that diagnosis, a sample was sent to our colleagues in the mitochondrial lab, and I'll tell you about that, what that means in a minute. And they found a spelling mistake in the mitochondrial DNA in David, which is the reason for him having Lee's disease. It also, in fact, they went to check your blood sample, which you sent in through the paediatric team, and they found that you also have a spelling mistake in your mitochondrial DNA. Now, the reason for all of those lost pregnancies, and something you've probably already worked out for yourself, having had these problems with different partners, that this might be something to do with you. In fact, mitochondrial problems are very unusual, because normally we get our genes from our mum and dad. We get instructions, our genetic instructions, a copy from mum and a copy from dad, and they come in matching pairs. But there's a small group of genes which are different, and they're carried on a tiny chromosome called the mitochondrial chromosome. Now the mitochondria, in order to explain what they are, I've got to take you back a step. Your body's made of cells, millions and millions of little cells, each with a little wall around them and each with a job to do. There might be a heart cell, a brain cell, a skin cell, and they work as a team together to make the different organs. Now inside each cell there's a nucleus, and inside the nucleus are the instructions that tell that cell what to do. But around the nucleus there is the factories that actually do the work, that make the proteins that make your body work. And what makes them work is that they have an energy supply from things called mitochondria. The best way to think of them is to think of the batteries in a dictating machine or something, the things that make it, or a radio. The mitochondria are the energy source inside your cells. Now, what makes them very special is that all the mitochondria in my body and in yours, all of our mitochondria come from our mothers. Because when an egg and sperm meet, the sperm is very, very tiny and has a set of chromosomes in it, the genetic material. The egg's a big, enormous thing full of lots of information, including all the mitochondria. So if there's anything wrong with the mitochondria in the egg, then that will be passed on to the baby. But if there was anything wrong in the mitochondria of the father, he can't pass it on. He doesn't pass on the mitochondria. Okay, so it exclusively comes down from the mother's side, and it can affect either boys or girls because we all need mitochondria to make us work. The reason mitochondria are special is we think in evolution, a long, long time ago, billions of years ago, there were cells and there were bacteria, and some of the bacteria went to live inside the cells. That made the bacteria safe because there were walls around them, and it helped the cells because it gave them energy. And so the bacteria kind of were like tame sort of cows being, in a milking herd, if you like. They provided a source of energy and were protected for it. And gradually they lost their independence and became part of us. And the only difference is they still have this little tiny chromosome that produces a few dozen messages, especially for making mitochondria. So in your mitochondria, there are lots of mitochondria that have a spelling mistake in them. And just by chance, your ovaries happen to have a sort of concentration, we think, of those cells. So a lot of your eggs are being produced with mostly faulty mitochondria.
Okay.
Does that make sense?
Yes.
So that means every time you get pregnant, it will be with an egg that might contain faulty mitochondria, and it doesn't matter who the father is because the mitochondria are exclusively coming down in the egg.
Okay.
The problem is we can test a pregnancy, but we can't easily say what proportion of the mitochondria are affected. So it's quite hard to predict the effect, but your experience suggests that you've got a very high risk of either losing it or having a baby with a problem.
I was going to say, what was your opinion based on the 7 instances so far?
Well, I mean, it's pretty obvious that so far it hasn't worked out very well, so there's a very high risk of a recurrence of either a lost pregnancy or of a severe disability, and not something we can easily test for and make accurate predictions on. What we can do, however, is involve you with the IVF clinic, because you would be an ideal person to go for an egg donation. And if we went for an IVF pregnancy whereby you got given an egg by somebody else, it would be fertilised with the sperm from Dom and then put into you. And in fact, you don't need to fertilise it outside. You could just put the egg and the sperm in together and let them do their thing. And there's a good chance then you get pregnant. And of course, that would completely sidestep this problem. But in every other respect, it's your baby. So we've actually fixed the problem by taking away your egg and putting in a replacement egg. Now, genetically, it will not be your baby, but biologically, it would be your baby. You carry it to term. And so in every respect, it would be your child.
Okay.
Mitochondrial inheritance is one of the most challenging things to explain to people, not least because it's very hard to give them any precise figures and accurate results. But it is important for people to understand that you can go for ovum donation, and the attraction of ovum donation is that it doesn't carry quite the same emotional problems as sperm donation, because the mother is still obviously the mother in biological terms, and a lot of people see that as a very attractive option. A common reason for referral to the genetic clinic is the birth of a child with a malformation. Some of these have a specific diagnosis, but in most cases we have to rely on empiric recurrence risk figures based on large-scale population studies. Birth defects involving the heart are the biggest single category. Selena, Dominic, thanks for coming along. My name is John Byrne, I'm the consultant in clinical genetics. The cardiologist sent me a letter asking me to see you in the clinic. Can I ask, was it your idea or their idea that you came to see us?
It was their idea.
Okay. So, I know that you've lost a baby with a heart problem. What was the baby's called?
David.
David. And how long is it now since David died?
It's 6 weeks.
Okay. Now, I had a detailed explanation in the letter from the cardiologist that David had a really very, very complicated heart malformation. So the arteries were the wrong way round on his heart, and there was also some valve problems, and there was nothing they could do to repair that. So what are the questions do you have in terms of looking forward to the future?
Well, do we know why that happened? That's the first thing.
Okay.
And obviously we would like to have children, so is it going to happen again, and is there anything we can do about that?
Okay. The difficulty with this is that David clearly had nothing else wrong with him apart from this very severe heart problem. He looked the same as all other babies. We've looked at his chromosomes and they look fine. So it looks to be what we would call an isolated malformation of the heart. And the difficulty is that we know that there is a genetic contribution, but it's not a simple genetic trait where you can give very precise figures of it happening again. So what we've done instead in this situation is we've looked at lots of families like yours and compared them, looked at them as a group, if you like, and said, okay, what happened when they had further children? And so the fancy word people use is an empiric recurrence risk. It's not based on any sort of theory, it's just simply looking to see. If we collected 100 families just like you and looked to see what happened to the next baby, we can then use that as guidance for you. Now the answer to that is that congenital heart problems are quite common. In about 1% of all babies will have a hole or a murmur or something. And about 2 or 3 per thousand will have a quite severe heart problem. Now, in your case, having had one previous baby with a complex heart defect, the chance of it happening a second time is about 10 times higher than the general population. So it's about a 2 to 3% risk of recurrence.
Why is that?
Probably, in fact, we're fairly certain it's because of genetic factors. So if you look at a variety of evidence, it suggests that it's a mixture of genes from both sides. It's not a single gene that's causing the problem, but it's a mixture of certain genes working together that predispose to the heart going off course in its early development. It's a very complex process, turning this simple tube into a 4-chamber heart. It's almost surprising it doesn't go wrong more often because it's such a complicated sort of folding bit of origami. We are working at the moment in research to try and identify all the genes that are responsible for this, and we'll probably end up being able in the future to do tests to predict who's at higher risk of having babies with heart problems and who isn't. But at the moment we can't do that because it's just too complicated. We haven't found the underlying cause. But the 2% figure is a real figure, so there have been hundreds of people just like you gone on to have another baby and they had a 2% recurrence risk. Now the problem with that figure is 2% sounds quite a low risk to me, but you've lost a baby. So when I say there's a risk, even if I say it's 1%, 0.5%, the word risk kind of echoes, and you think, well, knowing my luck, I'll be the one. You can't. It's almost the reverse of winning the lottery. Once it's gone wrong, you feel like it's going to happen again. You have to try and break away from that a little bit and sort of be objective.
I suppose because there's always risks anytime anyone gets pregnant.
Absolutely. Everybody's got about a 2% risk of something going wrong of one sort or another. This is a sort of extra couple of percent because of your past history. But if you turn that on its head, that means there's a much better than 95% probability that if you got pregnant again, the baby would be fine. And I think that's the important way to look at it. Turn it around and think of this as a positive, not as a negative.
But when you say that you take it empirically or from other cases, then there is a chance that it's just something that we don't know about yet, or you haven't discovered yet. Or...
That's right. I mean, so the possibility is in that crowd of 100, there are some people who've got a high risk, where it's actually maybe 1 in 10 or 1 in 4, and others where the risk is actually almost none at all, but they kind of mix together. All I can do is give you the mixed risk, if you see what I mean, that at the moment I can't tell you apart from the crowd. So it's a 2% is an average risk. The other important thing to say is, of course, we can look at the baby's heart on the ultrasound and reassure you early in pregnancy that everything is going according to plan.
Okay.
And it does also give you the option, if the baby's heart were to be severely malformed, not to carry on the pregnancy. So that kind of gives you that, if you like, that umbrella that allows you to try again, because at least you know that you're going to get to see the baby's heart developing early on, and you still have the option not to carry on if a problem developed.
Okay. Let's say that we do get pregnant and we are unfortunate enough to lose another baby, to be in that 2%. On trying for a third time, would that percentage increase even further?
Yeah, because that would actually, if thinking about that crowd scene, if you've had 2 babies with a heart problem, that kind of puts you into another group, a smaller group, where again, if you look empirically at that smaller group who've had 2 previous babies with a heart problem, then their recurrence risk is at least 10%.
So it's not
Because
the
it's telling you-
it's not the act of having a baby that increases the risk. It's
That's
just
right.
putting us
It
into
just
a new group.
it picks you out of the crowd. It tells us something about your genetic makeup. If something's happened more times, it means you're probably more genetically susceptible than the next couple. It's just that you look alike. We all look alike. We can't tell those people apart from the crowd until it's happened.
Okay.
But as things stand at the moment, your risk is relatively small. And as I say, the take-home message is that the chance of you not having a baby with a heart problem is more than 97%. People don't feel lucky when something's gone wrong, and so it's very important to give risk figures every way around. If you say a 1 in 30 risk, that sounds high. If you say a 3% risk, that sounds a bit better. If you say 97% probability that it'll be okay, that sounds much better. And given that people are feeling negative about their chances, it's perfectly reasonable to present it in that slightly more positive light, because that kind of balances up their thought process. Genetics is often in the news, so it's useful to know how to deal with interviews on television cameras. The next section addresses this problem and shows you how you might do it and how you shouldn't do it. There's been a lot of debate in recent months about the use of human embryos for research. We're here in Newcastle upon Tyne University to talk to Dr. John Byrne about their work in the discovery of cells which can be used to treat a whole variety of diseases which have been taken from human embryos. What exactly has been discovered? What the team in Newcastle have succeeded in doing is managing to grow embryonic stem cells. Now, these are the cells from the very earliest stage of development which are capable of turning into any different tissue, liver, heart or kidney. And having those cells in the laboratory means we can start to tease apart how the genes control the early steps of development to hopefully in the future be able to develop treatments for a lot of chronic diseases. So how do you know that these cells really are stem cells? It's difficult to prove that stem cells really are stem cells, and in fact the line that's being grown in Newcastle is the only one in the UK where that's been established. The only way you can do it for certain is to inject the cells under the skin of a mouse that has no immune system. Now that strain of mice is held by some research laboratories around the country. It doesn't hurt the mouse, but obviously it has to be killed at the end of the experiment. And looking under the microscope at those small tumours, you can see that these cells have grown into what's called a teratoma. They can be heart cells, kidney cells, liver cells, all jumbled together. But that means they've got the absolute capacity to turn into every type of tissue. What will these cells be used for? None of the stem cells so far produced in the world can be used to treat anyone because they've all been developed using mouse cells to support them. And you can't put into a human being a living tissue which contains a mixture of animal tissues. In the future, we'll develop ways of growing these cells without mouse cells, and then they can be used to treat a whole range of diseases. We already use stem cells, of course, in the form of cord blood samples to treat bone marrow failure in babies. And the hope is, and the expectation is, that these cells will be used to repair damaged spinal cords from road traffic accidents, to replace the dead cells in someone with diabetes to allow them to make insulin, and to repair someone who's got cirrhosis to give them new liver cells. So a whole range of potential treatments in the future. Do you think there are any ethical problems with the work that you're doing here? There's been a great deal of debate about the ethical challenge of this type of work. The fact is that the very early embryos from the fertility programme, which were used to develop these cells, had already been set aside and were not going to be used to make someone pregnant. So basically, taking those cells was very like taking a transplant donation from someone who'd been killed in an accident. What we've done is grown out cells that will take us towards being able to treat people in the future. So we think ethically it's an entirely defensible thing to do. And of course the British government have ruled that this is permissible under the Human Fertilisation and Embryology Authority's guidance. In fact, the only real ethical debate in the UK is likely to be the fact that we have to use mice in the research programme to prove that they are stem cells, but unfortunately there's no way around that at the moment. This is Erwin Thompson for the Channel 16 News. There's been a lot of debate in recent months about the use of human embryos for research. We're here in Newcastle upon Tyne University to talk to Dr. John Byrne about their work in the discovery of cells which can be used to treat a whole variety of diseases which have been taken from human embryos. What exactly has been discovered? Well, what we've succeeded in doing is culturing under standard laboratory conditions a pool of embryonic pluripotent or indeed possibly totipotent stem cells from an unwanted blastocyst at the 8-day stage, which is actually quite important because that's post-gastrulation and therefore at a relatively late stage compared to the level at which other people have done this. And how do you know that they are stem cells? Well, we know they're stem cells because we've actually used a whole series of classical surface markers, the TRA160, that's the tumour rejection antigen 160, which we know is specific to pluripotent cells, and the SSEA4, which has also been identified as a very useful surface marker of pluripotent or indeed possibly totipotent cells. What exactly are you going to use these cells for? Well, I'm not exactly sure what we'll be using the cells for yet. I mean, there is a plan to create a stem cell bank in Cambridge, and we'll be donating ourselves to that, of course. And we have lots of plans to examine the differentiation pathways because it's very important to understand the transcription factors which initiate the development of different tissue types from these stem cells. And we hope that research will lead to some very fruitful consequences in terms of a whole range of therapeutic possibilities. Do you think there are any ethical problems with the work you're doing here, Dr. Byrne? Obviously, any research of this kind does just generate a whole variety of ethical problems in the mind of some. I mean, I have to say that we feel that it is ethically acceptable to work with these cells and that there is great potential benefit, but of course one is not an ethicist and therefore one cannot state unequivocally that this is not a source of some problems, but we feel very happy with the work that we're doing. This is Erwin Thompson for the Channel 16 News. People who themselves have a genetic disorder face particular problems when it comes to dealing with the risks of their family. My close friend and colleague Tom Shakespeare is a sociologist who was born with achondroplasia. Here he talks about his experience when he and his wife came to the obstetric clinic. Tom, thanks for coming along. Can I start by asking you, when you first realised that you had achondroplasia, when did it first become obvious to you that you were a bit different from other people?
I can't really answer that, John. I mean, what you have to realise is that if you're born with an impairment, it's always part of your life. And in addition to that, my father also had achondroplasia.
When you came to get married yourself and think about having kids of your own, what were your feelings about that? Were you worried about it or were you content? I mean, how did you cope with that?
I'm not sure if it was clear cut. I mean, obviously, again, if you've lived all your life with an impairment, in many cases you're not going to see it as a problem, or at least you're going to be realistic about the extent to which it's a problem. You know that it involves certain amounts of social stigma, maybe a degree of pain and inconvenience, but you know on balance that it doesn't make a big difference to life. So I don't think I ever felt that I shouldn't have kids because of achondroplasia. I suspect if I was being entirely honest, at the back of my mind, I hope they wouldn't have achondroplasia, because it makes life more complicated and more difficult. But as far as I was concerned, and indeed of my partner, the risk was one worth taking, and we were going to be happy with either outcome. But what I would say is that even though they hadn't found the gene when my daughter was born, which is 8 years ago, even though there was no test, ultrasound screening obviously is and was widely used, and the pregnancy was scanned, considerably more than a as it were unaffected pregnancy would be. So we knew.
Was that at your request, or
no,
was it
not
just
at all, not at all.
Showing an interest.
More than an interest, I would say. We were obviously knowingly entering into a risk situation. We'd already decided that that wasn't a problem for us, and that the pregnancy would go ahead, whatever.
And did you feel under any pressure from the obstetricians to sort of, if it was abnormal, you might go for termination?
I think so. Despite the fact that obviously I was clearly affected, and clearly in a sense unaffected by the condition. The fact that they arranged 3 or 4 scans instead of 1, the fact that they pointed it out on the screen and said, well, yeah, look, and then there was a sort of, as it were, pregnant pause in terms of, right, what are you going to do about it? And we went, fine. And they went, but look, and we went, fine. And then there did seem to be a level of scepticism on their part that we really knew what we were doing, or that we were really happy about it, which seems to me to be extraordinarily arrogant, considering that we were mature adults, and indeed that I personally was obviously familiar with the situation.
Humour can be very powerful in getting messages across. A few years ago, Tom Shakespeare and I recorded this little clip to illustrate the challenge of termination of pregnancy.
You should have been terminated.
You what?
You're not normal.
Well, what do you mean, not normal?
You got achondroplasia.
Achondro what?
You got a G to A, position 380 in your FGFR3 gene. You're not normal.
FGFR3 gene? So you don't have any dodgy whatsits yourself then?
Well, I might have the odd recessive gene. Everybody's got one of them, but yours is dominant.
Dominant, and you don't have any dominant genes?
Well, I might have the odd dominant gene for something like dementia or something like that.
Nothing serious then?
Well, it's serious, but that doesn't come on till you're old.
So you couldn't have been terminated then?
Well, you could.
You could?
But you wouldn't want to.
No.
Because, I was able to be a doctor and have kids and things.
What, like me?
Yeah.
Right.